Welcome everyone. In this video, I will talk about how commercial aircraft manufacturers integrate the propulsion system from the design level to the entry into service. For the convenience of a larger audience, I will keep this video as basic as possible. I'm sure you're going to like this video. It is a very interesting subject of interest, I think, especially for the aviation fans. Also, I have divided this topic in two parts, so make sure you do not miss anything. In this part of the video, I will talk about the pre-development stage. Please note that we will not look at engine assembly systems specifically because integrating the propulsion system requires a multidisciplinary approach, so we will try to understand the bigger picture behind it. So let's start. So before jumping on the actual methodology of integrating a propulsion system to an aircraft, let's just review what we know about the modern commercial aircraft engine in context of this topic. Here we look at the major components of the overall system. Engines, including their own systems, have valves, fuel and oil pump, and engine control computer. Engine buildup has hydraulic system, electric generator, engine bleed for cabin air conditioning and fuel line. Pylons are structural link between the engine and the wing. All the forces are transferred through it, including the engine thrust that propels the aircraft. All systems are routed between the engine and the aircraft and host certain equipment such as fire extinguishing bottles. Propulsion systems integration within the aircraft takes into considerations like avionics, an interface with engine computers, propulsion system cockpit controls, and propulsion system displays and warnings. The cells and its design considerations are aerodynamic, air conducting through and around the engine, acoustic attenuation, ventilation, thrust reverser, which is an engine mechanism to decelerate during touchdown, and anti-icing system to protect the engine. I will not be explaining here how the jet engine of a commercial airliner works, as that is a separate topic altogether. I will do a video on that in future, but for now, let's just have a look at the basic structure of a turbofan engine. So we can see from this animation that the air is passing through different components, starting from a fan, followed by compressor stages, and combustion chamber, where the air-fuel mixture is burned to generate thrust or expanded work through the turbine stages. They are basically connected on a power shaft. I guess some engineers may not be pleased with my technical description of their beloved engine, but remember I have done this to stay on the present subject of interest, and I will just state that the engine provides the required thrust that helps the aerodynamic forces at play to achieve a sustainable flight. A quick fact check here. I know many people might be knowing this, but many won't. The aircraft engine is nothing but a gas turbine. Yes, technically they are not so different from the ones used in the electric power generation plants, but due to some complexities, you can literally count on your fingers the number of companies that manufactures aircraft engines. Aircraft manufacturer cooperates with both the engine and nacelle manufacturers to ensure the final aircraft meets regulatory requirements as well as its own program objectives. Take the engine oil tank as an example. This is not just the responsibility of the engine manufacturer and is dependent on several aircraft parameters such as operation, flight time, and cockpit indication, as well as engine constraints like oil consumption and pump behavior. The propulsion system, including the engines, nacelles, and pylons, and the controls integrated into the aircraft, has a significant impact on the aircraft's safety, its economic performance, as well as its environmental and acoustic efficiency. Fuel burn, for example, makes up 40 to 50% of an aircraft's cash operating cost. Operational performance, reliability, and direct maintenance costs must also be taken into consideration. This makes engine manufacturers a natural partner in aircraft development, who provide valuable input from a very early stage. Before launching a new program, a joint study will enter a decisive pre-development phase, which will define the following aspects: choice of propulsion architecture, including turbo machine and nacelle, engine integration, including mounting concepts, aerodynamics, and aircraft systems such as electrical, pneumatic, and hydraulic systems, and avionics. Aircraft and engine optimization to achieve the right balance between takeoff performance, climb, and cruise performance, as well as acoustics. Once the key characteristics are settled, aircraft manufacturer involves the nacelle manufacturer in a three-way discussion with the engine manufacturer to finalize the overall concept for the integrated propulsion system. Pre-development steps towards product definition, aircraft parameters, and engine key design space parameters, then the progressive extension of design space to a wide array of parameters and constraints. To explain better, I have made this map from an article in the Airbus magazine. In this map, the interrelated parameters and variables are represented by 3 loops of different colors, and 3 set of parameters are also represented by 3 different colors. The parameters that are independent are mentioned outside the loop boundaries. The loop number 1, which is represented by the dark green color, contains the parameters of the engine in pink and aircraft in sky blue. MTOW stands for maximum takeoff weight. The loop number 2, which is represented by the olive green color, builds on the parameters of loop 1 with adding more parameters and variables like fan diameter and climb for the engine and landing gear length, engine positioning, wing dihedral, wing area for the aircraft. Finally, the loop number 3 is completed with the addition of parameters like time on wing, span, and mission evaluation, which is a parameter for aircraft and engine represented by the deep blue color. The independent considerations are aircraft technology level, climb profile, bleed architecture, which is related to eliminating air from fuel lines, idle movables architecture, flight level, and Mach flexibility, which is related to stable speed variations according to specific conditions, cruise, growth capacity, engine commonality, aircraft commonality, market sector, mission mix, fleet mix, and engine technology level. This pre-development phase usually takes around a year, but can last longer for a completely new aircraft model. The aim is to finalize a robust engine, nacelle, and integration concept before agreeing a development plan, which includes design, testing, verification, validation, and maturity. Both the engine and nacelle manufacturers make commitments on key performance and economic elements, enabling aircraft manufacturer to provide all aircraft guarantees to its customers. This process is similar to both completely new aircraft engine configuration and a new engine option developed for existing aircraft. With this, we have come to an end of this part, and if you like what you have seen so far, then please stay tuned to this channel for the next part that I will upload soon. This is Aditya Chaudhary signing out. Cheers and have a good one.